So welcome to the next webinar in my series on modern Java by example. What we're going to do today is we're going to continue our discussion yesterday about timed Memoizer implementations, except now we're going to take a look at the use of a periodic application of the scheduled executor service, whereas yesterday we had taken a look at a one-shot mechanism that used scheduled executor service. So the things we're going to see here, we're going to see the periodic use of scheduled executor service to schedule things that run periodically, schedule events or runnables that run periodically. We're also going to take a review back on the concurrent hash map and the features that it has in terms of compute-if-absent, which we've seen many times before, the clever remove approach, that's another one of these atomic checked and act operations, and we'll also see the use of AtomicLongs. I had some good questions come in yesterday about certain choices about using one synchronization mechanism versus another. So as I go through the code, I'll also clarify those things as well. So let's take a quick look. Let me go ahead and share my screen, and let's go ahead and take a look at the location of the code. So the code, as always, is in my GitHub repository, and it's down in the Reactor EX3 folder again. I've been improving this implementation day by day, so every day things get a little bit better, and hopefully today is no exception. So I think you'll enjoy what we cover there as well. Let me see if I can make sure that this is looking good. I think it looks all right. So let's now go ahead and switch over, and we will look at the code. So the code we're going to cover here, we'll just start quickly with a recap of what we covered yesterday, but I'm not going to dwell on that because this is the second time in a row we've talked about this. So the actual interesting stuff takes place in the run method, which appears down here. And you can see that run goes ahead and makes a Memoizer. We'll look at that in just a second. It then goes ahead and tests the program using the Memoizer that we chose by the factory method. And then we go ahead and make a copy of the contents of the concurrent hash map in the Memoizer so we can print it out later. And we shut the Memoizer down. And you'll see more specifically why we have to shut the Memoizer down, because in the background, the Memoizer has a scheduled executor service instance running in its own thread of control. And so we want to shut that thing down so it doesn't keep spewing diagnostics out on the screen after we no longer care about getting the results. So that's the main thing we're going to focus on. I will also come back probably tomorrow, and we'll take a look at some new back pressure and concurrency stuff I added to this example. I'm not going to go over it right now, but I added some new features so that you can now have multiple threads subscribing to process the prime numbers in parallel. And this was in response to a question I got the other day about how do you scale this up. So now you can have one publisher thread and then n subscriber threads that are doing the processing and running in parallel. So we'll probably talk about that tomorrow, because I want to use that as an excuse to talk even further about other advanced mechanisms for back pressure and flow control in RxJava and in the Project Reactor. So let's sneak into the make Memoizer factor method. Yesterday we talked about untimed Memoizer. Very simple. It's really just a thin wrapper around a concurrent hash map. Then we also talked at length yesterday about timed Memoizer, and that was the variant that did a one-shot registration with a runnable for every key value pair that's registered with the cache. And if you go back and watch the video from yesterday, you'll see what we do is it schedules it to run at some point in the future, let's say every 400 milliseconds or every minute or every day or whatever the periodicity is. And when the timer goes off for each pair, then that pair is checked to see if it was accessed during the period of time when the timer was active. And if it was active, we keep it and we schedule it to run again in the next period. If it was not active, we purge it, we get rid of it. And I mentioned the problem there was you end up with a lot of runnables registered with the scheduled executor service. So for every key value pair, at some point you'll have a runnable scheduled, and that could become very large. So what we're going to do today is we're going to look at a different implementation that uses so-called timed Memoizer EX. And this implementation is going to be very interesting, and it'll show off a bunch of other cool features. And I think it'll also give you a better sense of how the whole approach for timers work in Java. And this is a concept that's important not just for things like Project Reactor or RxJava, but just in general when you want to write programs that depend on time. Okay, so let's go take a look. Here is the timed-memoizer EX class. As you can see, basically it implements a timed-memoizing cache. And the way that the cache works is every so often it will purge stale entries. And it's only going to use one runnable to purge them all. So that's like one ring to rule them all, one runnable to purge them all. Under the hood, as we'll see, it uses the ConcurrentHashMap function, which is kind of the workhorse for these types of mechanisms. It also uses the ScheduledThreadExecutorService, which is a scheduled executor service implementation, except it's using it in the periodic fashion. And then it also uses a Java AtomicLong. And I want to clarify when we get to that point why we're using AtomicLong here, as opposed to some other synchronizer, say something like a Java long adder. And there's reasons for doing that. Okay, so let's dive in here. You can see that as we did yesterday, we're going to have a way to keep track of the timeout in milliseconds. As with yesterday, there's one field that's used for all the various key value pairs that are registered. So we have one timeout for the whole timed-memoizer EX object. We could make it more fine-grained if we wanted to, and I'll leave that as an exercise for the viewer. We also have a concurrent hash map. This concurrent hash map looks very similar at first glance to the one we had yesterday. It maps keys to ref-counted values. But just for fun, I did a little different way of doing the generics here. So ref-counted value in this example is now a generic type, and that allowed me to do a couple other things we'll talk about in a second. And the ref-counted value class is actually implemented slightly differently as well, because we no longer have to schedule each key value pair individually. We just schedule one thing. It's called the mpurge entries runnable. So that's the concurrent hash map. Here is ref-counted value. You see that I made this a static class. The one we looked at yesterday was a non-static class, and I parameterized it by type V. And I just felt that that made it a little bit more clear that it was a generic type, whereas before it was a little unclear. As before, the fields are identical. We have an AtomicLong, that's the ref count, and we have mValue, which is a field that's of type value V. Those values are set by the ref-counted value constructor. So V is assigned to its field, and we use the initial count to initialize the AtomicLong. Now, the reason I use AtomicLong here is because we're using an interesting feature of AtomicLong that'll show up in a second, and it's basically get and update. And this is a way of being able to get the current value and then make some change to the current value and atomically update the new value with whatever value you want to give there. That could be a function or could be related to the current value. There is no such mechanism in long adder. Long adder is really stripped down, and really long adder is primarily used just to be able to keep track of statistics, mostly for things like web counters in web servers to see how many times you've been accessed and so on. So it doesn't really quite give us the level of precision that we would need in order to make it work effectively. So that's why I'm using AtomicLong. People have pointed out, which is correct, that if you have a very highly scalable system, that AtomicLong might have more contention than long adder, but it doesn't really matter because it doesn't have the features that we need anyway. Of course, you could probably re-implement this to not need those features, but so far I like the way it works, and it doesn't seem to be a bottleneck by any means. Okay, so now let's come down here and we'll take a look at the equals method. This is the same as yesterday. Two ref-counted values are considered equal if their ref counts are the same. And that may be a strange definition of equality, but the way that we use this is very clever, and we only need to do comparisons for equality in sort of one circumstance. And so that's why we're able to do this the way we do, and you'll see how it gets used in a second. Then we have increment and get. This is the method that's called when an entry is either first added to the map or whenever the application is applied. And what it does is it increments the ref count by 1 and returns the value. And we use that ref count incrementer as a way to know whether something is fresh versus stale. So if something has been incremented during the time period, we consider it fresh because someone cared enough about it to change it or to access it. But if it wasn't accessed in the time period, we consider it stale and it gets thrown out, gets evicted. And then there's another method called get that just returns the value without doing any atomic long manipulation at all. So why do we have that funny equals implementation? It's for this purpose down here. We have a field called m non-accessed value. And we use this as a flag to indicate whether something's been accessed or not. And m non-accessed value always has a reference count of 1. So once the reference count is set here in its constructor, it's never changed. And so we're going to see in a minute when we take a look at how this schedule mechanism works and how the eviction checking mechanism works. We're going to try to remove a key from the map. And if the key that we're removing has a value that's equal to the m non-accessed value's ref count, we know that it wasn't accessed during the time period that matters, during the elapsed period m time in milliseconds, time out in milliseconds. So that's why we do things like that. Now, you'll also start to see things. So what I've shown you so far is very close to what we did before with the original timed memoizer, with one exception. We don't have a schedule method in timed memoizer EX. The ref counted value does not have a schedule method. And that's because we're not scheduling timers on a per key value pair basis. We have one and only one timer scheduled. Well, as you might expect, that change has some other side effects that are important as well. So in particular, we have this couple of new fields here that were not in the timed memoizer version, and they're very, very interesting. The first one is something called a threshold crosser. And we need this kind of funky, cool little helper class in order to determine when we go from no entries in the map to at least one entry in the map, and also when we go from at least one entry in the map to no entries in the map. And that threshold crossing needs to trigger certain actions. And you'll see when we show the code here why we need to do this. And it has to do, as always, with avoiding race conditions from non-atomic check then act statements. So we'll show how that gets used when we get a little bit further down. But threshold crosser, as you can see, starts out with an initial value of 0. Another field we have here that's different from yesterday, we have something called a scheduled future. And a scheduled future is what you get back when you schedule a runnable or a callable with the scheduled executor service to run periodically. So when you schedule something that's going to run periodically, you get back a scheduled future. I think you actually get back a scheduled future even if you do it for one-shot scheduling. But for what we're doing here, we need this scheduled future so that we can cancel the timer mechanism when the number of entries in the map drops to 0. Because if there's no entries in the cache, there's no sense trying to purge anything. That would make no sense. So you'll see how we need to keep track of this future so we can basically shut down shut the map down, or shut the scheduling service down when we need to do it. Okay, now we get to the main driving force in this particular implementation. And this is a single runnable called m-purge entries. And unlike the version we looked at yesterday, where we had to have a anonymous inner class runnable because we accessed the this pointer, this time we don't need to do that because we're not accessing the this pointer. So we can actually make this just a good old runnable. This is a runnable lambda. And the syntax may be a little bit jarring at first if you're not steeped in the black art of lambdas. But basically, we're just defining a runnable, and here's the run method that we're defining. So as you can see, this particular method is going, or this particular, well, this is actually the run method. This is the lambda expression for the run method. We print a little diagnostic saying we're about to start the purge of all the keys that haven't been accessed recently. And then what we do is we go through the concurrent hash map, and we're going to use the for each method. And for each on a concurrent hash map, we'll just walk through the map in basically iterator order, and it'll give us back key value pairs. And of course, we can do this using the cool lambda expression syntax. If we wanted to, we could also expand it to look like this if you like more explicit, say, somewhat verbose code. But in this case, I think it's pretty clear what's going on. So you get key value pairs back as lambda parameters. At first, things look similar to what we did before. In fact, a lot of this looks quite similar to what we did before, but you'll see there's a few differences in the implementation we're looking at. First thing we do is we take the reference count of the current value that we're inspecting. So this is what we're going to call old count. And then we attempt to remove the key. Now, the way this works, the remove method, the two-parameter remove method on concurrent hash map is one of those cool check then act methods. And what it does, it atomically checks to see if the key has a value that matches the parameter that we're providing here. So we're passing in the m non-accessed value, which has the reference count of 1. So if the reference count of the value associated with the key equals the m non-accessed value's reference count, we know that this particular value and key pair has not been accessed. And you'll see later how we know that. But we know that because if it had been accessed, its reference count would have been greater than 1. So if it hasn't been accessed, we're like, boom, you're out of here. So we go ahead and remove it, and we print a diagnostic saying that we're removing it. Here's where things get really interesting. So at this point, let's say in this particular path through the code, we've removed the item, and now we have to make a decision about what to do. So if the act of removing the item caused the count to go from 1 to 0, in other words, if there are no more entries in the map, then we're going to go ahead and cancel the scheduled future. Because as I said before, what's the point of doing this purging if there's no entries in the map, right? You're just burning CPU cycles completely unnecessarily. So how do we do that? Well, the obvious sort of naive thing to do would be to say something like, if the count, here's the obvious bad thing to do. Do not try this at home. This is a bad idea. If you want to get yourself into trouble, write code like this. If mhash.size equals 0, then mScheduledFuture dot cancel. True. Do not write this code. It's very tempting to write this code. Chaos and insanity will ensue because, of course, this is a non-atomic check then act operation because we're checking to see if the size is 0, and then we're doing some other operation. But there's no synchronizer that's being held across those two checks. So you absolutely cannot do that. And if you try to do this, your code will work 99.999% of the time. And the one time it really matters, which is the customer demo or when you're controlling the nuclear reactor temperature or whatever, it's going to fail. And then chaos and insanity will ensue. So do not write this code. Instead, what you need to do is do something that will be run atomically. And because I didn't really see anything obvious that could work this way, I wrote my own little class, which is the threshold counter. And the threshold counter basically has a method called decrement and call at n. So remember, we started off giving the threshold counter, the crosser rather, the value of 0. And every time we're going to go from 0 to 1, we're going to do something. And every time we go from 1 to 0, we're going to do something. So decrement and call at n says, if the count goes to 0, that's the n, then run this action. So let's go ahead and take a look at the threshold crosser. So here's the threshold crosser. It's a really simple little clever class, little helper class. It keeps a count, which you initialize here. And the count doesn't have to be anything fancy. This is not going to be accessed concurrently. And so, well, it is accessed concurrently, but it's done in a way where we're going to protect it. So we don't have to make this an atomic int or anything, atomic integer. So as you can see here, here is decrement and call at n. We have the synchronized block that's held, which means this is guaranteed to run atomically with respect to all the other threads that may be calling into this method and the other threads that are calling into this method. And we're going to decrement the count. And if the count reaches the value that we pass in this case 0, then run the runnable action. So as you can see here, what we're saying here is if the count goes from 1 to 0, we now no longer have any entries there. And so we're going to go ahead and atomically call cancel on this. So there is undoubtedly other ways to do this, but I thought this was kind of clever, and it seemed like a reusable class that might be beneficial to leverage elsewhere. So I put it in here. So in that case, we've removed the element, and if that was the last one in the cache, we canceled the timer. What happens, however, if this item we're looking at had been accessed in the last period, so we don't want to remove it? Well, what are we going to do then? Well, first we're going to print some diagnostics. Then we're going to make sure our program actually works. And the final thing we're going to do here is very much like we had done yesterday. We're going to take a look at the current value of the reference count for this value. And we're going to use get and update. And this is one of the main reasons why we can't use long adder here, because it doesn't have this kind of a mechanism. So get and update is an atomic check and act method, which will give back the current count, which in this case would be whatever it is. And if the current count, which is the count that is currently in the AtomicLong, is greater than the count we got up here when we came into this block of code, if that's the case, then we're going to make the current count the count. What that means is that between the point where we got the old value and where we're going to do this update, some other thread has come along and accessed this key. And because we're never locking the entire critical section in order to minimize contention with a shared lock, in this particular case, we need to check to see if the count has changed. And if the count has changed, it meant somebody was interested in this particular key. So we're going to give it the benefit of the doubt. We're going to say, you know what, you're scot-free for the next period. Nobody has to access you, and you're still considered live. So in that case, we're going to give current count. Otherwise, if there was no change in the counts, we're going to give it 1. And 1 is basically just resetting it and saying, okay, you know, you have to keep your fingers crossed, Mr. or Mrs. Key, that you get access. Otherwise, you're out of here the next time we go around. So that's basically how we do this. And this is more or less the same that we had done yesterday. And that's, again, why we don't use long adder, because they don't have that mechanism on long adder. Okay, so that's the purge entries runnable. And we only need one of these things with this implementation, and you'll see why in a second. Now we have the scheduled executor service. This is the thing that's going to manage the timeouts. And here is the timed-memoizer EX constructor. So it's going to call up to the superclass to initialize the function field, do a little sanity checking to make sure that we've given it a positive timeout in milliseconds value. Otherwise, it wouldn't make any sense. And then we're going to go ahead and create a new scheduled executor service. And once again, we're just going to have one thread, because we only need one thread to do this. And we're going to make the thread that it creates using the thread factory have a name, which we call Reaper, and we're going to make it a daemon thread. And a daemon thread simply means, as we talked about the other day, if this particular thread is the only thing left running in the program after the main thread exits, the whole program will shut down. If we didn't make it a daemon thread, then it would cause the program to continue to run, which is probably not what we want to have to do. Okay. Then we go ahead and cast the scheduled executor service field to be a scheduled thread pool executor, which it is, because that's what we initialized it to be up here. And then we go ahead and set the policies correctly. So when things get canceled or when things get shut down, they don't stick around, and the scheduled executor service forgets that they ever existed, which is exactly the behavior you most likely want. And for some very strange reason, that's not the default behavior for scheduled thread pool executor. So we had to make that tweak ourselves. All right, at long last, we're really here to talk about the final interesting method in this class, and this is the apply method. And this method is quite different from the one we saw yesterday. So I made a few other changes because I just am getting more enamored with kind of breaking the code up so you don't have lots of lambda expressions just sitting out there by themselves, which are kind of hard to follow. Not as easy to document, not as easy to understand. So we're going to define a function called mapping function. And the mapping function takes a key and it gives back a ref counted value. And of course, this is what's going to get called if there's not already a value for a given key. This is the mapping function that ConcurrentHashMap is going to use to do all the dirty work to compute the result and do other stuff. So here's how this works. This is kind of cool. So when mapping function is called, and it's going to get called down here under ConcurrentHashMap. So actually, let me show you this first. We come in this method, ComputeIfAbsent gets called with the key that's passed in as a parameter. If that key already has a value, then we get it back. Otherwise, the mapping function is called. What is mapping function? This is mapping function. So mapping function is a function, a functional interface function in modern Java terms. So what we do is we take the key, K, and then we go ahead and call the increment and call it N method. This is one of those threshold crosser methods. And what this does is if the incrementation, if the atomic incrementation of this count equals the number we passed in, which in this case is 1, then we're going to run the action. And this will all take place atomically, of course. So this code here is an atomic check then act operation, which is precisely what we need to have to get the behavior correct. So if we went from 0 to 1, in other words, if this is the first entry that's being added to the cache, or if the cache was canceled earlier because it didn't have any entries and now we're adding in the next one back, then we want to go ahead and run this lambda runnable. And you can see what we do is we do a little sanity check just to make sure that we haven't gone awry and had our scheduled executor service turn to null. And assuming all is well, we then go ahead and we schedule with our scheduled executor service the mpurge entries runnable that I showed you a moment ago, and we schedule it at a fixed rate. And I probably could do this at a fixed delay. That might actually even be better. We'll talk more about that in a second. In fact, probably should change that to be fixed delay. Let's just do that. I'll talk about the differences between the two in a second. So what this basically says is call this entry back this many milliseconds into the future. So in m timeout milliseconds, call it back. And then if we use at fixed delay, it says, and then after we finish running this thing, then wait up to m timeout in milliseconds time, or wait at least that amount of time, and then call it back again. So we'll keep calling purge entries periodically. That's why it's a periodic scheduler as opposed to a one-shot scheduler. Keep calling this event back until we tell it not to, until we cancel. And we cancel, as you saw, when the number of entries in the Memoizer cache in the concurrent hash map falls to 0. So we keep going, we keep calling back until then. The difference between at fixed delay and at fixed rate is fixed delay starts calculating the delay after the callback finishes. So after the callback is done, then we do the next one. At fixed rate says, I will keep calling this thing back even if it isn't done at the fixed rate. So, like 100 times a second or whatever. So if we have a large number of entries in our map and we have a long delay, we might end up actually having multiple things going on, and that would cause chaos and insanity. We don't want that to happen. So we're going to use at fixed delay. I think that's a better choice here. Of course, if going through the map doesn't take very long and you have a long enough timeout period, it doesn't really matter which one you use, but at fixed delay is probably safer. Okay, so that's how we're going to start the timer system working. And you can see this is a periodic. So I should probably say, to periodically purge keys not accessed within the timeout in milliseconds. Let's see. All right, so there we go. And so as you can see, we give it the initial timeout and then the periodic timeout where it'll be called back and over again until it's canceled. Then the last thing we do here is we go ahead and keep in mind this is still all part of this mapping function. The mapping function will then go ahead and return a new ref counted value that applies the function that was passed in originally. This is like the isPrime checking function to the key, gets the value, and then that will go ahead and be stored in the map at the key, and then that will be returned as the result. So that's how we kind of kick things off. And then if you look down here, so that was just defining that function. Here's the little piece of code that says ComputeIfAbsent key mapping function, which I think hopefully is clear by now. And then what will come back from that will be a ref counted value. And then we go ahead and say increment and get the ref counted value. And increment and get on the ref counted value will increment the reference count to give it its initial count of 1. And then it goes ahead and returns that value. So that's basically the way things work. And it's kind of interesting to go back and look at the two implementations, the timed-memoizer and the timed-memoizer-EX, because one of them uses the periodic mechanism, which is more complicated to start and stop, but you also don't have to have this complicated schedule method that gets called over and over and over again every time a key value pair times out. So what you end up with, in some sense, is only one entry in the scheduler, in the scheduled executor service, versus n entries in the scheduled executor service. But that one entry does a lot more work. So let me show you kind of how this works. Let me just demonstrate how it runs. We'll go over here and we'll take a look at the program. So I've got debugging turned on. Right now I have parallelism turned off for reasons we'll talk about later. I have the, just for kicks, I turned off back pressure, so the data is just going to be blasted through. And we're going to generate 10,000 keys, and I think they're up to something like 10 million or so. And we're going to choose the X parameter. That means use timed-memoizer-EX. And then over here, we're going to do a new thing. I came up with this really cool, fun debugging tool that makes it easy to kind of showcase exactly what I want to be displayed. And this is called a debugging tag. So I want to basically show the output from timed-memoizer-EX. And so if I set all those flags and I go ahead and I run the program, it blows up. Whoops. Let me go back and change that back. I don't want to see fixed rate. I will fiddle around with that later. So we go ahead and run this program, and as you can see here, what it's going to do is it's going to schedule the purge entries one time, and then you get a little callback from the Reaper thread when the timeout period has elapsed, and it goes through and it purges all the entries. And you can see that it purged a whole bunch of them. Some of them it didn't purge. Some of them were still active. You can see that too. And keep in mind that this is the single-threaded version of the whole thing. And you can see that it actually does multiple passes. So it purges everything once, then the timeout period elapses again, it purges them again. So it makes multiple calls to purge the entries. In fact, let's see, looks like actually quite a bit of entry purging going on here because it's running for quite a while. And then let's see if we can find the end. In fact, it looks like it's still going. I think the reason it's still going is because I'm not running this with parallel processing. So I probably gave it a very large number of elements, and it needs to, it's doing it all in one thread, the poor system. Let's see if we can kind of speed this up a little bit and make it run faster. So over here, let's set parallelism to true, and we will see, and then let's also give it a parallelism count of 3. That means we're going to have 3 threads in a pool processing these things. So that, oops, that blows up. I probably gave the wrong parameters here. Let's see. Let's try this, see if it's any happier. So now it's basically doing things in parallel, and hopefully it won't take quite as much time to run because these things are running in the background and it's not trying to use one thread for the whole thing. So anyway, this thing is chugging away, doing the processing, and as you can see, the difference here is it's doing them in phases. So every phase or every epoch, every time period, it goes through and it goes ahead and purges everything that's there. So I'll let that keep running, and then we'll go back and, whoops, maybe it just finished. Nope, still chugging away. So we'll wait and let it run and come back. So there was a couple more things to look at here real quick. So the remove method is used to remove the item from the cache. And all we do is we look it up by the key. That gives back a ref counted value, and then we get the value from the ref counted value. So that's how we remove something. We get the size of the cache just by calling the size method on the concurrent hash map. And then the get cache method works like the one we did yesterday. We make a new concurrent hash map, which we call cache copy. And then for each element, each key value pair in that hash map, we go ahead and put it into the cache copy. And of course, we take the key, because we got the key, but we have to get the value from the value, because it's a ref counted value. And then we return that. And then shutdown goes ahead and resets the initial count, shuts down the underlying scheduled executor service, sets it to null because we're no longer doing anything, and then we clear out all the keys that are in the map. Let's see if it ever finished running. Yep, finally, so it finished running the version that's the, it finished running the version that was using the Memoizer. Now it's off chugging away on the non-Memoizer version. And of course, the non-Memoizer version won't do any caching at all because it doesn't have a Memoizer. It just goes ahead and recomputes the prime check every single time for every single key. Okay, so that's pretty much what I wanted to cover. Like I said, we'll cover some other things in our next session that are interesting, talk more about back pressure, but I wanted to give you a sense of some of these advanced synchronization features and how to use them with Java. So let's go ahead and take some questions. Let's see. All right. In the threshold crosser, do we need to call action inside synchronized? Yes, that's the whole point. If you don't call action in synchronized, then it's not an atomic check then act operation. It would be a non-atomic check then act operation. It would be check atomically, whatever that means, and then act non-atomically. And then you'd end up with opportunities for race conditions to sneak in. When the thresholder API is called, the other threads could still put entries into the cache. So all we care about is whether we're going from 0 to 1, right? Or 1 to 0. And the reason is we don't want to end up losing either purging this thing or not purging it. So if somebody else, if we think we're going from 1 to 0, then we're going to atomically do that operation. We're going to cancel it. And then at some point later, someone else can come along. They're going to also have to call this same operation. So this operation always gets called. So it's the point where the behavior has to go through. So we don't have to worry about race conditions there. Likewise, when we want to go from 0 to 1, we just want to make sure that somebody has reestablished the purging mechanism. Someone else has scheduled the mechanism. So I don't think there's any race conditions there. Let's see. So next question is about the mechanisms having to do with the get and update call on AtomicLong. If the current count is greater than the old count, we want to make sure the key is not purged earlier than m timeout value. So we reset the count to current value. Yeah, so what's happening with the atomic long? Let me go ahead and share my screen and we'll talk about that again, because that's an important subtlety to understand, and it's definitely pretty subtle. All right, we should be back in the code here. Let's see, this is up here in the purge entries call. So if you take a look here, you can see that this is where we're doing this. So remember, we grabbed the old count up here. So we got the old reference count. And then down here, we're going to update the reference count. Now, we could just say, hey, you know, if somebody else comes in the meantime and updates that value, you know, you were within microseconds of, these are very, very fast operations. This is probably going to be microseconds or nanoseconds. So it's like, oh, well, no big deal. We're not going to give you any credit for being accessed. And it's not the end of the world, obviously, if the cache is going to be purged, because if this item is purged from the cache, because next time around, we'll just have to put it back in there. It's not like it's going to be incorrect behavior. But what we're doing here is we're saying, you know, if you did get accessed again in that period, we're going to give you credit for it. We're going to give you the current count. And when you give the current count, and obviously the current count is going to be greater than 1, then we want to make sure that you stick around an extra time. So we're just trying to give these key value pairs the benefit of the doubt to make sure that they can be accessed and live as long as they ought to. So that's the reasoning behind that. So what's the schedule at fixed delay versus schedule at fixed rate? So schedule at fixed rate says, make this callback, 100 times a second. It doesn't matter how long the callback actually runs, and that's where the kicker comes in. So let's say you want to do callbacks 100 times a second, but something that you call back takes longer than whatever it is, 10 milliseconds or whatnot to run. If the callback takes too long to run, while the callback is still running, the next callback will be called back. And now you'll have two callbacks going simultaneously, which would cause all kinds of confusion from unexpected race conditions. So what schedule at fixed delay says is, when the callback finishes, then start the next callback at that delay from that point. So it's the difference between starting the timer, when something finishes, versus saying, I'm going to call you back at a fixed rate that never changes, even if it takes longer than expected. And you can think of all kinds of analogies in everyday life where you really want to be, you want the meter to start ticking when you start something, and you don't want to be charged for stuff that you shouldn't have because you didn't get a chance to finish the previous task, those kinds of things. Does the size API get the correct value? So it depends what you mean by the right value. So let's go ahead and take a look at what you're referring to here. There's an excellent video by my buddy Doug Lee, who wrote large swaths of the Java concurrency and synchronization mechanisms, and it's called something like engineering concurrent components in Java or something like that. If you Google Doug Lee engineering concurrent components, I think you'll find his video. And his point in there is that all the methods on these concurrent classes lie. That's his term, not my term. So whenever you go to the concurrent hash map and you say, what's your size? It's always lying to you, right? Because the moment you call that method, in between the time when you call it and it comes back with whatever the current value is, it may have gotten larger, it may have gotten smaller. So it's always telling you something that's an approximation. So that's exactly what we're doing here. The call to mcache size, of course, that value is a safe value, and you can see how it works, actually. It computes a sum count, and then it goes ahead and returns the appropriate result. And I bet if we look at sum count, it's doing a bunch of magic stuff, and it's also working on long operations. So I think there's some magic going on. But you can see that they're not going to go to heroic lengths to give you 100% precision because it's always a lie anyway. So that's what you're getting. You're getting back whatever the concurrent hash map thinks. And again, that's why we have this threshold crosser, so we can be more precise about how things work. Let's see. It would be interesting to compare this Memoizer implementation to the Guava cache implementation. Yeah, I don't really have much experience with the Guava cache implementation, and I'm not sure if it's trying to solve the same problem. This whole implementation was originally inspired, not this implementation, but the concept of an untimed memoizer came out of a code snippet in the Java Concurrency and Practice book by Brian Getz and Associates. And they do something very, very much like what you see here. In fact, what's interesting is if you read the Brian Getz book, they actually implement this using future task, and it's a really cool implementation. But that book that they wrote, Java Concurrency and Practice, predated Java 8 and, quote, modern Java. So they had to use future task because there was no ComputeIfAbsent method in Concurrent Hash Map at that time. Since that point, they've added ComputeIfAbsent to Concurrent Hash Map. So many uses of the Memoizer that they used there would be less necessary. But when I read that book, I thought, wow, this is pretty cool. What would happen if we tried to add timing support to it? So the timed-memoizing is definitely something that is not what you would find in the Brian Getz book, and then there were different variants of that. Is get snapshot based? Is get cache snapshot based, or it's the live view? Well, this is the magic, wonderful thing about. Let's see. Let's go back to the time memoizer example here. this is the magic, wonderful thing about Concurrent Hash Map and its whole synchronization mechanism. Nothing is ever locked down. The map is never locked entirely. And so this is just going to be whatever the heck comes out when we go through this thing and make a copy. So you could have other elements added in the meantime, and all that the cache guarantees, all that the concurrent hash map guarantees is the values you get are not corrupted, but there could be other values added. It never locks the whole thing during the duration by design. So it's always, it's an approximation. For this particular program, it doesn't matter because we don't call the get cache method until we're done with the processing. And so we should hopefully not have to worry about things changing out from under our feet. Although I guess I should rephrase that. Let's go back and look at this real quick. This is kind of interesting. So, I wonder if the program ever finished. Yep, the program finally finished. And as you can see here, the Memoizer version was just a tad faster than the non-Memoizer version, even though the Memoizer version was spewing out all of those print statements. So I think that gives you a sense it probably was actually a bit faster because it was also paying the cost of having to do the print statements. So what I wanted to show you, however, was notice that we had, lots and lots of values. We checked, 9,897 prime numbers ended up in the map at one point or another. But at the very end, we only had 159 of them left because it had been purged. And to the question about whether you get a snapshot or not, here's the code that we do. So we come over here, we run the tests, we get the cache, and then we shut down the Memoizer. So if we had shut the Memoizer down first, the cache would have been empty, so we would have got nothing. But notice when we do the get cache call, there still could be things running in the background in parallel at that point. And so as a result, what we get here just is basically a snapshot of whatever it is at that particular point in time. And obviously, if you don't like that, you'd have to put other synchronization in to give you more guarantees. But that's just kind of the way you work with things like concurrent hash map. Again, it's approximations, unless you go to the trouble to fully synchronize something, which is, of course, what we do with our threshold crosser. Okay, well, thank you guys so much, as always, for coming. Let's see if there's any other, there's another question. Can we have concurrent implementation of weak hash map that will take care of purging stuff? I don't see why not. You could try experimenting with a different implementation. It's easy enough to plug in the concurrent hash map that's used to create the implementation. So you could certainly take a shot at trying that. So please feel free, as always, to experiment with different ways of modifying this code. So what we're going to do tomorrow, assuming I can get my act together in time, is the following. Let me reshare my screen. What we're going to do is we're going to revisit the main program here. Now that we've done a sort of a detour into timed-memoizer internals, which are, I think, pretty cool. We're going to come back and look at the driver program, which I've kind of blinged out a bit to make run concurrently, and we can control a lot of the options and see what the benefits are of doing this. And you can run it with 12 threads versus 1 thread for the subscriber and see what the speed up is, and so on and so forth. We're also going to play around with other back pressure strategies. So the back pressure strategy we used last time, a couple days ago, was the strategy that was based on hybrid push-pull back pressure, where you ask for a chunk and you get a chunk back. What we're going to do is then look at some other strategies, which include queuing and include dropping. And obviously, you can queue stuff up to a point when eventually you run out of space, in which case you should either use the push-pull model or you should give up and drop. So we're going to look at those other alternatives. And really, the bottom line comes down to what kind of data do you have and how important is it to make sure you don't lose any of it, and how fast are your producers, your publishers, how much horsepower can you throw at your subscribers. These are some of the considerations to take into account when thinking about the right mechanism to use. So that's what we're going to talk about tomorrow. Obviously, in the meantime, I will re-render the video, I'll render the video and upload it. I've got a new webcam, which works really well when I'm recording stuff. So the video I put out yesterday had super high definition quality, but I've discovered if I use it as my webcam that there is a noticeable lag because the processor just can't keep up when I'm webcamming at the same time that I'm recording. So sometimes if I do the recordings offline, then it'll turn out to be super high quality. Other times you just have to put up with the standard definition quality that we get here, because otherwise my lips and my voice are completely out of sync and there's jerky behavior on the screen and so on. But again, thank you guys so much for coming. Great questions as always. And if you have anything else you want to ask about or share or inquire about, please feel free to post it to the YouTube comments section and I'll get back to it just as soon as I can. So thank you.